speak quickly.
Yes.
Okay? And don't be excited. Everything is okay.
Yes.
Okay. Now it's well. It's online. לא, תגיד לו שסתם אמונה הוא מחפש אותו. שתדע לו להיזהר. אוקיי. להתראות. So everything is okay, right?
He's not showing me my notes.
You need the pointer, and the pointer is very important.
Yes.
So the pointer, everything.
I don't know. I also would like if I made the point of making notes, then I would like to see that.
I don't know what to say. So where is he now?
I don't know. He just disappeared.
Okay, I will try to find it. Okay, but you have this one. This is better than the pointer. אבל יש זה יותר טוב. This is much better than pointer. And you have to really do everything that you show. Don't do it with you because nobody can see it. Just go to the point and show the point, okay?
Okay.
With this one, okay?
Yes.
Everything. Then you show the diagram. So this axis, this data point, and so forth, okay? And I will try to find it. Good morning. איפה אתה? אז מה, הגעתי למכון הביולוגי. אמר לי שם מישהו, הוא שאל אותי מי זה, זה שלומי, אמרתי לא, זה סלומון אבני. אבל הבן אדם לא יודע אפילו מי זה סלומון אבני, אתה מבין מה אני הגענו? בקיצור, תבוא להרצאה. מי שמדבר? תבוא, אולי מישהו יוכל לשאול את זה אינטליגנטי. תבוא, תשאל שאלות בצורה אינטליגנטית. יאללה, להתראות.
חזרנו...
I will phone to Batya.
I mean, the person was just here.
I know, but he disappeared, you see. I phoned to the secretary and asked her.
כמה צריך להוסיף לדעת אם בכלל יש קש.
פשוט אני מחפש את הבחור הזה, התלדפי,
אהלן.
הוא היה כאן לפני רגע, הוא הלך.
What do you mean?
We're going to presentation here.
משהו שקשור שהיא החברה הייתה רוצה לראות כאילו מה שהיא כותבת, היא יודעת איך לראות את זה על המסך. שהוא יבוא, זה התפקיד שלו, זה הכל. לא, הוא סידר את המצגת. אוקיי. You know how to do it? Here, you see it now.
Yes, but my computer can do it, but it shows the presentation
your
on
computer,
this.
your computer is a new one.
Go.
My computer can do it also.
But this one shows the same.
That's the situation. Rita, everything is in your head now.
Hey, you don't need to see all of it.
Yaki can tell you. הרצל, הכל בסדר, הוא הסביר לי את העניין. יש אישור בחטיבה.
Do you have a connection to this?
אבל אל תעזור שאתה מצגת שנייה אחת לפני הרצאה.
אף אחד לא אומר שום דבר, מה אתה רוצה?
נכון, הוא לקח אותי למחסור פורטך כלימד, אבל הוא הולך איתנו אתמול לחורשת הירח, לגמרי.
מה, את באת לחורשת הירח ולא נכנסת אליי הביתה? קיבלתי אישור...
הייתי מודחת לך.
קיבלתי אישור להיכנס לחורשת הירח?
יש לפחות הכי טובות שזה לא מופרע.
אני לא יודע, דבר עם איתן, אני, מה שהוא אמר אני עשיתי. הייתי בסך הכל...
את קיבלת אישור להיכנס אני לא שואל אותה, ישו, אתה בכלל לא שואל אותה מצווה אישור להיכנס לשכונה שלנו.
אבל יעל, את גם גיאולוגית. מה היית איתן?
אתה רואה מוטי, אתה לא צריך לנסוע בכלל...
אפשר להראות לך, מה שהיה שם היה הפסידו. הוא רצה בגלל...
זה הפעם השנייה שאנחנו שם מתקיימת לשבוע האחרון, כי דגמנו שם מים לפני...
אספנו לו גם דין נבירות, הוא רצה עם נבירות, את הדולרית מהנבירות. הוא רצה גם דולרית מסיבית.
Do you just come down? Something like a remote to the slides? Do you want?
הוא לא בירך אותך. היא לא בירך אותך. אין אימייל.
I think I can also do it with it. I think I can do it also with the computer and the pointing stick.
היא אמרת כשאמרת את זה, אמרת רק בזמן.
כן, זה היה
מה שהוא רוצה.
תן לנו עוד 5 דקות, מה יש לך?
לא שלחתי לה.
אפילו ביבי בא.
לא שלחתי
לא שלחת אותה בחכם,
אבל שלחתי ולא לא שלחתי.
רגע, אז מה בשלחת? אתה מתנפל.
It worked all the time.
Just a second.
I tried it several times like this and it worked perfectly.
Yeah, but I don't have connection. Oh, you have, okay.
That's the point of another.
I see, I don't understand all these new things. Okay. Okay, perfect. Shall I bring you a remote?
Yes, yes.
I'll do the same German, langsam.
Yes.
That's fine. You would be fine. Yeah.
מה זה בייס?
לא יודע אם זה עוזר, זה עוזר ל5 דקות. מה אתה מחפש להיות?
This you have a laser issue. Okay, so go.
Okay. Good morning. So it's always, I think, very happy to present a PhD student that arrived to the final stage, or almost the final stage of the thesis of the dissertation. And this morning, I'm really very happy to present Rita Fuchs. Rita came to us from Austria, from this beautiful city of Graz. And it was within the framework of a big project which was called the Baseline Earth. And Rita will tell about this project. And right, Rita had to deal with different kind of things in Israel, especially here in the campus. One is two jackals that were trying to attack her once. So she overcame these two jackals, and she overcame Boaz and myself. So it means that she could achieve something. Rita, go ahead.
My talk will be on strontium isotopes at the onset of the ice ages. And my PhD was part of a European project, which was the Baseline Earth project. And it is on brachiopods, which is the B over here. And it is on brachiopods over the entire Phanerozoic time. And brachiopods, to use them to reconstruct the seawater composition and see what we can get from the brachiopods and the seawater composition that we have. And this project was initialized by the Geomar, which is in Germany. And the idea came then because they got hands on Jan Weiser's collection. And Jan Weiser used his collection to construct an 87 strontium, 86 strontium curve all over the Phanerozoic. And to be precise, all of this, what I have marked here in orange here, is made from brachiopods. And what you can see here, this part is not from brachiopods, it's from foraminifera, because here we start having trouble finding enough brachiopods. They are not very frequent in the Cenozoic time. And then there is another curve, which is the second set of isotopes that I want to use. That's the delta 8886 strontium curve, which is from another group. And what you can see here, they also worked with brachiopods, and they had trouble finding enough samples even at earlier times. And then again, we have a huge gap here because people could not find enough brachiopods. And my PhD comes in here. I want to fill in some data within this gap, to be precise, for the last 6 million years. And if we zoom in on those 6 million years, they are very interesting because we have a major climate transition where we have two cooling events that mark the onset of the ice ages. And for this curve, you can see here we have the 87 strontium, 86 strontium all over this time frame. But we have the delta 88, 86 strontium, just a recent value, and we don't know anything about the ice ages. And this is kind of problematic because you can tell a lot from the strontium isotopes, and I will explain this to you immediately. And this is because the strontium isotope system, it has 4 stable isotopes. which you can see here. And from these 4 stable isotopes, we use 3 of them, which are these 3, and these give us 2 different ratios. The first one is a well-known one. It's the radiogenic 87 strontium 86 strontium ratio. And the idea here is that we have several input fluxes, where we have an original signal that comes from the circulation of seawater through the mid-ocean ridges. And then we have an altered signal, where we have radioactive decay of 87 rubidium that is enriched in the continental crust. And this gives us 87 strontium, which then is enriched in the continental crust. And then everything, all strontium that comes from the continents, is enriched in 87 strontium. And the mixture of these 2 then gives us the 87 strontium, 86 strontium ratio in the ocean, where we have then 3 possibilities to use it. The first one is that we start guessing how much comes from here and how much comes from here. The second one is that if we already know this ratio and we know how it evolves over time, then we can look at our samples and then use this 87 strontium, 86 strontium ratio for dating. And the last one is if we already know the time and if we already know what 87 strontium, 86 strontium composition we are supposed to have, we can look at our samples, and if it's the same, then we can say, okay, this is perfect seawater composition. And if it's not this composition, we can say, okay, maybe we have diagenesis, maybe we have continental influence, maybe we have ABC. And the other ratio that we have is the stable delta 88-86 strontium ratio. And you can see already here, this is in a different notation. It's a delta notation because the differences are very small. And delta notation means we normalize it to a standard and then we multiply it by 1,000 so that we can actually see something with the differences. You can see here this was not necessary in the 87 strontium, 86 strontium ratio because these fractionation ratios are much smaller than what we get from the radioactive decay of the rubidium. And here the idea is that we have input sources that are lighter than ocean water. And there we have, again, strontium that comes from the mid-ocean ridges. Then we have strontium that comes from the continents, which means the granitic rocks. And then we have very light strontium in comparison to the others that comes from the dissolution of carbonates. And we can then put this in the river, and the river is already a bit heavier as the 2 input sources. If we then go into the ocean, then we start in the ocean, we start to precipitate calcium carbonate, and the calcium carbonate is comparatively light, which means we enrich the ocean in heavy strontium, and we have a heavy strontium composition of the ocean, which means that we can tell from the interplay between these 2, the lighter input and then again light output, how much are we putting in compared to how much are we taking out. So this gives us additional information to the where does the strontium come from that we had with the 87 strontium, 86 strontium ratio. And here comes now the reason why I am focusing on the ice ages. And the reason for this is that we have a weathering pulse hypothesis. And I showed you before a graph where the 2 sources were more or less equal. But when people looked at it, then what I show you here, that the 2 sources are actually not being equal. And we are getting, at the moment, more strontium from the continents than we can balance with the 87 strontium, 86 strontium from the mid-ocean ridges. Which means if we compare these 2 and then we do a calculation, we find we don't get the same evolution as we are seeing in the seawater. And the reason for this is that they think that we have additional strontium coming at the moment in because we are having an interglacial. We had a glacial before. We ground all of the material with the glaciers, and then we remove the glaciers, and now we can chemically weather all of the fine material that we got from the glaciers. And then if this is true, then this started with the onset of the ice ages, and the 87 strontium, 86 strontium is supposed to go up with the start of the ice ages. And With the stable delta 88-86 strontium, the system is also not quite working out. And here the theory is that we have more input at the moment from the continents because of this fine material. But also, we need additional material also during the glaciers, where before we said that we will be getting less from the rivers, but we need another source that will come from the continent, but it should not add more 87 strontium, because we are already too heavy. So it has to be a carbonate source, which is on the first, it's very light, and on the second, it will not impact on our 87 strontium, 86 strontium budget. But the thing, of course, with this flux is that until now we don't have data 88, 86 data from the ice ages, which means that we don't actually know whether this flux exists or not. So on the whole, if these two hypotheses are true, then the delta 88, 86 strontium value is supposed to decrease during the interglacial, and it is also supposed to decrease during the glaciers. So if we have a look at an evolution over time, and if this is the seawater, then the evolution is supposed to be something like this. If we have 88, 86 here, 87, 86 here. And this is now what I want to go and test, so this is my main goal that I want to go and test. And because I cannot use the real seawater, because the seawater is gone, I will be having to use shells. And so my first sub-goal is that I have a close look at my shells and see that I'm measuring a real signal and that I'm not having any measurement artifacts. And the second sub-goal is, which I explained to you before, that we are not having enough brachiopods in this time frame. And for the brachiopods, we know what is the difference between the brachiopod and the seawater. But for many other species, we don't know what is the difference between the species and the seawater. So we'll have to find this difference for a few other species so that I can go and reconstruct the seawater curve from these species. And for this sub-goal, I took some recent samples from Israel. And these samples are from a cruise offshore Israel. Those are pectinid samples. And then I have a second set of recent samples. Those are gastropod samples, and they are from the beach of the IUI in Eilat. And then, of course, I also need the samples for my main goal. And these are from an outcrop that is located in Italy. And it is located, to be precise, close to Milan. It's called the Stirone River outcrop. And at the time that I was having a look at it, it starts as a very deep water section, so it starts at the transgression after the Messinian event, and then it is several hundred meters deep, and then it shallows up until this point in the middle Pleistocene, where you see it's already very close to the shore. And where you can see here, it's a river outcrop, which means you can go from here, these are the oldest parts, and then you can go towards the youngest parts inside the river. And you can see here, this is these are the strata. And you can see here you can just walk through the river and take your samples. And these are the samples. You can see here they are very well preserved. And this is one more sample that I got there. And the section is well dated only in the upper part, somewhere here. And so I will show you a few places which can be used to orientate on in the lower part of the section. And the first one that is important is the Miocene-Pliocene boundary, that is at 0 meters. And from here on, we are having homogeneous clays till about here. And here we have chemoherms within the homogeneous clays. Then we have a bioherm, which you can see here. And from here on, we are getting more shallow, and then we can see actually the layers and the bedding, and we also get more fossils. Up here, we have a bed with a lot of thalassinoidous trace fossils, and these have been filled with flint So it's a very prominent feature. And just 40 centimeters above, I have chosen a bed which has a lot of fossils in them. And on this, I will do all of my studies where I need several fossils for one bed, from one bed. So I will now start with the first sub-goal, which is the choosing of the correct and best samples. And this is also part of the Baseline Earth project, where there was the idea that maybe the animals, they go and they calcify, which means it's not a chemical calcite, it's a calcite from an animal, and it can be different between different species. And also, there can be different mineralogies. Not all the animals are doing the same mineralogies. Different mineralogies also have different properties and different chemical compositions. And these different mineralogies, we can even have them within the same shell. And the next thing that can happen is that we have shells with numerous voids, and that we have to avoid contaminating our sample with sediment that can be inside these voids. And the last thing that may happen is that we either go and have diagenetic replacement of the original shell, or that we have a lot of voids in the original shell and that we have precipitation of diagenetic calcite within these voids. And that was the first thing that I wanted to check on, that this isn't happening. And for this, I used a diagram where I have here the 87 strontium, 86 strontium composition of the sample that I have versus what is supposed to be the seawater composition at that time. And what you can see here is that most of the samples are very close to the seawater line, or they're within area of the seawater line. And that there is a second set of samples that has a different 87 strontium, 86 strontium composition, and a different calcium over strontium composition, where we have a mixture of another signal here. And this mixture is mainly in one animal, and these are the Ostraedulis shells. And then I wanted to know what is this second source, what is this second signal. And if I looked at it, it's a signal that is very enriched in manganese. And manganese is an element that is normally mobilized in the anoxic environment. Since animals generally don't strive in the anoxic environment, it means that everything that has a lot of manganese in it has to be precipitated after the animal has died, which means that it is a signal that we don't want, which is the reason why I removed the oysters from the survey. And the next thing that I wanted to check on was biocalcification, where there was the general idea that if we have our animals, where these are brachiopods and some equipecten, Crucimeris, and here the oysters are still within the survey, then there is supposedly good parts and bad parts of the animal. What is supposed to be a very bad part is the primary layer of the brachiopods, also because it is very often genetically replaced. And so I scratched it off from the shells for the scalpel. And then there is other parts which are supposed to be not good because they're precipitated very fast when the animal is being young, and because they maybe they precipitate, then they are dissolved, and then they are precipitated again, which is the muscle scar. So these are these two things. This one is the young part of the animal, and that's the muscle scar that's supposedly precipitated and then dissolved and reprecipitated. And these are supposedly out of equilibrium and give us supposed to give us a different signal than the other parts. And what you can see here, that actually we don't find such a different signal, although there is definitely two different groups in here, and that's a calcite group and an aragonite group. So the main conclusion from here is that we can use all of the parts and we don't have to think about where they come from, but that we have to think about whether they are made from calcite or from aragonite. And the next thing that I needed was the difference between the species and the seawater, which is called the big delta. And the reason for this is that we have the brachiopods, where we know the big delta, and we have other animals that we that I want to use, which are, for instance, the pectinates, and where we don't know the big delta, and we cannot assume that these two big deltas are being the same. And for this reason, I started off with fossils and recent animals. For the fossils, I took brachiopods, and from this, I know what is the difference between the species and the seawater. Therefore, I can calculate the seawater from them. And for the others, I know already what is the composition of the seawater, which means this is the Yapsu seawater standard, as it is taken from the literature, the established one, and this is the Yapsu that I measured with my samples. You can see they're pretty much on the same spot, which means also that my measurements are being good. And so I used brachiopods and several other organisms, namely foraminifera and glycimoris, and then several types of pectinates, recent ones and fossil ones, and then recent gastropods from my lab. And then I went and had a look at the brachiopods, and I knew what is the difference between the brachiopod and the seawater, and I also knew what is the distribution coefficient between the brachiopods and the seawater, and from that I calculated what was the seawater at that time. And you can see here the seawater at that time was within error of the modern seawater. So for this reason, I'm not applying any corrections to the values that I have here, but I use them as they are. And what we get is that we have a difference of minus 0.14 between seawater and gastropods, and that the pectinates have the same difference of minus 0.14 to the seawater. And now, since I already have a lot of measurements, I wanted to know whether I can find any actual meaning for these measurements, because it's always good if you have an additional paper. And what I found was that if we go and plot the distribution coefficient and the big delta of the 8886 Johnson, then we have certain fields for chemical calcite, which these are data from Mahmoud and Florian Böhm, and for chemical aragonite, these are data also from Mahmoud and from Noah. And if the animals are plotting far from these two fields, then people have measured these animals, these coccolithophores, and assumed that these are not sitting on these two fields because they don't precipitate from seawater, but they take out single calcium and strontium ions from the seawater and then move that to a vacuole, and only then they precipitate their coccoliths and move them up. So they think what we see here is not actually the precipitation mechanism, but the fractionation that happens here. And if that is true, then with other organisms, this should be different, which means that if we have corals, which you can see here, they're sitting in the chemical aragonite field. And then there is Jonathan's group who worked on corals, and they say that corals are actually precipitating the aragonite from seawater. And we can do this also with more groups. You can see here foraminifera. They are also sitting on the chemical calcite line. And if we look at the precipitation mechanism of the foraminifera, they bring small parcels of seawater to the calcification site. Well, here they calcify and then they move on these small vacuoles. The next one that we have are mollusks. So these are my data. You can see they are not sitting on the chemical calcite line. And if we have a closer look at those, then according to some papers, at least some of the mollusks are precipitating from a fluid that originally they derived from seawater, but they have a very complex mechanism of precipitation, and apparently the fluid that they have inside here is not not so similar to seawater anymore. And the last thing that we have are brachiopods. You can see here they're sitting on the chemical calcite line. Up until now, there is no literature on how they're actually precipitating, but from what we have seen here so far, I assume that the brachiopods are precipitating the calcite from seawater. So to conclude, we can use the stable isotope to trace and to distinguish between seawater and other types of transport. The brachiopods probably precipitate from seawater, and mollusks probably precipitate from a fluid that is involved from seawater. And then there is some further conclusions for my further study, which means that brachiopods and foraminifera and corals are reliable samples that I can use for my further study. Then the pectinids and the gastropods are all in a very tight range together, so I can still use them to get an 88-86 ratio of seawater from these animals. And then you can see here that there are some guys that are going all over the place, which are the coccolithophores, and that I cannot recommend anybody to use coccolithophores to reconstruct delta 88-86 strontium of seawater in the past. So now that we are all set and I have everything that I need for my main study, I will now go and concentrate on my main goal, which are the stable delta 88-86 isotopes during the onset of the ice ages. And what you can see here, this is my section where we have some anchor ages, this one at 1.71 million years, then one at 1.59 million years, and then at the very beginning, where we know this has to be 5.3 million years, that's the transgression after the Messinian event. So approximately this will be the Pliocene, this will be the Pleistocene, and the first cooling is somewhere here. This is the average of my data, so I have something like an excursion over here. This is the Kuival seawater range that I take from Farrell, which you can see here. I have a lot of uncertainty in the age, which means I get a very big box. This excursion that you see here, and you don't see it here, is probably because we're a lot more precise in time, and then they are smoothing over the curve a lot. And these are the delta 80-86 values that I measured in my shells. And if I now go and use all of the big deltas that I have calculated before and that I have measured before, then I get seawater composition that is something like this. And we know what is the modern seawater. And what we can see here is that the delta 88-86 of the seawater during the last 5.3 million years was essentially the same as today. So if we now go to the first assumption that we had, where we say that, okay, the 88-86 strontium is supposed to decrease and then it's supposed to decrease again. And we look at the data that I have, and you can see here it's constant. And if we look at the evolution, which we said that it's supposed to go like this, and in reality it's just going up straight. So just in the 87-86 and not in the 88-86. Then we can assume that we will probably need to adapt this model somehow, and that we have to reconsider all of this, what we have said here before. And that's why I started some modeling to see where we have the error or where's the problem. And for this, I built on what was originally there, where people had a diagram where they had the delta 88-86 and plotted it versus the 87 strontium 86 strontium ratio that still contains the fractionation factor. Most of you will not be used to that because in the conventional one you remove that. And there we have a terrestrial input flux, which is somewhere here, and it consists of a riverine input and of the input that comes from fresh water that is moving into the seawater on the land. And the second input that we have is the hydrothermal input, the hydrothermal exchange. And there we have two different fluxes, and both of them are associated with the mid-ocean ridges, where we have one flux that is discharged on the ridge, and the other flux is discharged on the side of the ridge. But in both cases, we put in strontium with a certain concentration, we react it, and then we get out the same amount of strontium with a different isotopic composition. And the two together give us then the total input, which is somewhere here. And if we now go and then look at what is the seawater composition and the carbonate composition, then if we assume that the whole system is in equilibrium, then the input should be sitting here, the mixture between those two should be sitting here. And furthermore, if we want the total system to be in equilibrium, then the input should be the same as the output, which means it should actually be sitting here. And as you can see here, this is not the case. And in the first paper, Krappenhöft and his group said, okay, the reason is because we had another input flux that was during the glacials, and it was very different from ours over here because we had a lot of dissolution of carbonates, and they will make our input much lighter, and they will move it over here. And then another group came and they did a lot of research, and they said, okay, we found a new flux, and it's here, which is perfect. That's within error of the glacial flux that we needed before. And they called it the brackish groundwater flux. So what is this flux? We have the circulation. We have the input of fresh water from the continent, and we have the circulation of seawater, and then we have a zone where the two of them mix. And this is this brackish groundwater flux. And they assumed that in this zone we have a lot of reactions that will go and will change the composition of our strontium. But what you can see here, I have put here two arrows. It will change the composition of our strontium, but it will not change the amount of strontium that we have. So it's a flux that puts a new flavor to the strontium, but it's not adding new strontium. And if I now have all of this data, I decided that I go and check whether all of this is true. And so this is the model, the formula that I worked with, and that I checked on whether if we put in all of this and we take out all of this and we exchange all of this, we will actually get the strontium evolution over time that we have seen before. And what we can see here in the isotopes, yes, we get it. But in the strontium concentrations, we don't get it. So in this case, I started here and then I moved backward. And then looking at this, I decided, okay, I also do it the other way around. I don't just start at 0 million years and go back to 2 million years, but I will also go and start at 2 million years and model towards 0 million years. And if we do that, you can see here, these are the delta 88, 86 values, and these are the strontium concentrations. This is the direction. We start at 2 million years and we go to 0 million years. And you can see here, I'm losing all of my strontium before I get to the present. But you can also see here, this is not good for the isotopes. I get a mess in the isotopes. So therefore, I have a problem and I have to find out what it is. And I went back and checked all of the fluxes that I had. And I found that actually all of these fluxes, they are being well researched and I can rely on them. There's only one that is suspicious, and it's the new brackish ground water flux that I showed you before. Because in their model, what the people assume is that this mixing zone is a black box, which means we put in the strontium, then we don't know what happens, and then we get out new strontium. But in fact, there is actually a lot of research on the processes that happen in the mixing zone, and I will show you what this research tells us. So the first type of aquifer I will talk to you about are the carbonate aquifers. And for this, I will need the solubility product, which is the ion activity product of the solution, divided by the equilibrium constant of the mineral. And if the solubility product is 1, then the solution is saturated, it is in equilibrium, and nothing happens. If the solubility product is larger than 1, then the solution is supersaturated, and the mineral will precipitate. And if the solubility product is less than 1, then the solution is undersaturated, and we dissolve the mineral that we have inside the solution. And what I will show you is the saturation index SI. It's just the log of the solubility product, and the translation is very easy. In equilibrium, when the solution is saturated and nothing happens, it's 0. If the solution is supersaturated, it's positive. And if the solution is undersaturated, it's negative. And now I go and take a carbonate aquifer and mix the fresh water and the seawater. And I look at the saturation index of aragonite in this process. And I start at the saturation at the equilibrium of calcite. And what you can see here, that I get a curve like this. So it's not straight. And the other thing is that although we start at saturation of calcite, at the beginning of the mixing, we dissolve both minerals. So I just have the solution of carbonates at the beginning of this mixing process between the fresh water and the seawater. Then I have a second zone where the aragonite is undersaturated and the calcite is supersaturated. And here I dissolve the aragonite and I precipitate calcite, which means I recrystallize the aragonite to calcite. And then there is a last zone where theoretically both of them are supersaturated, but in reality in seawater they are always being supersaturated and they never precipitate because we have kinetic inhibition by the magnesium ions that are in the seawater. And if I now go and look what this means for my strontium, then down here we have the solution of carbonates, and we add the strontium of the carbonates to the solution. And up here we have recrystallization from aragonite to calcite, where we have the strontium that is preferably in the aragonite, and then we recrystallize that to calcite, which means that we again add strontium to the solution. So we have two mechanisms here, and both of them add additional strontium to the solution. And the next aquifer that I had a look at was clays and clastic sediments, mainly because clays and clastic sediments are very frequent in the marine realm, where we have the interface between the fresh water and the seawater. And in these aquifers, what we have is ion exchange, which means that if we have a clay mineral, then we have an interstitial layer here, and here we can put ions. And we can put calcium and strontium, or we can put sodium. We will put calcium and strontium in the freshwater realm, and we will put sodium in the marine realm. And if we change, then if we go from freshwater to seawater, we will move out calcium. And if we move from seawater to freshwater, we will move out sodium. So the sodium that is inside here, when there is seawater, will be expelled to the solution, and we will put in calcium instead. You can imagine it somehow like this. We have the seawater first over here, and then we have a clay mineral that is full with sodium, and then we bring the fresh water, and then we start expelling the sodium from the clay mineral. So up until now, this mechanism is essentially neutral both to the total composition and to the strontium composition of the to the isotope composition of the strontium, because the isotope composition within the clay minerals is essentially the same as outside in the solution. It's just we are retarding or making faster the flux that is going to the sea. The one thing that can make a difference here is that if we move the calcium from the solution and we put it in the clay minerals, then we are missing calcium in the solution, and we can start dissolving carbonates with that. And this will give us an additional source of strontium for our budget. And the last one that I haven't had a look at was sediments that come from volcanic islands. And here we can have a riverine flux where we again have dissolved strontium in the river. But the river does not bring only dissolved strontium, it also brings a backload of particles, which are mainly glass particles. And these glass particles then start exchanging strontium with the ocean. And theoretically, what could also happen is that we then circulate seawater through the sediments, and then we can also get a new composition to the strontium. And for this one flux, I actually have a number. And if I now know all of this, I go back to my box model, and I decided that I replace this brackish seawater flux. It's definitely there, but it's apparently not there in the way that they described it in this paper. So I put instead a flux from the volcanic islands, which is an exchange flux. And then I found I'm still missing something, and then I wanted to find out how much am I still missing. And I find that I have a missing flux that is of carbonate composition. It's quite a large flux. It's a bit too large for just pure carbonate platforms alone. So that's why we need the additional dissolution of carbonates in the clay aquifers. And it's larger than the riverine flux. It's also larger than the hydrothermal exchange, but it is definitely smaller than the brackish groundwater flux that we originally had. So therefore, it is still a realistic flux, I think. And if I go back to my model, and I have this volcanic island flux, and I added the missing carbonate flux that I think it should be there, and I do this calculation again, what I find is that all of the isotopes and also the strontium concentration is coming out correctly. And this is then the diagram that we had before. And if I add the new fluxes that I found to this diagram, we find that the volcanic islands have essentially the same composition as the hydrothermal exchange, because it's in both cases basaltic flux. And that we have a carbonate flux that is somewhere here, and that this moves the total input towards here, where we have the output of the carbonates within error, and this is what we said that this is necessary to have equilibrium. And for the strontium budget, this means if this missing flux was not there, then we would have an evolution like this, which we don't have. We have something like this. And for the climate, this may mean that we also have a carbonate flux where we dissolve something and where we are actually putting CO2 into that. And as a summary, I have several main observations. The first is that stable isotopes in shells that precipitate from seawater have the composition of chemical carbonates that we expect. The next is that the delta 88-86 strontium ratios of seawater were essentially stable during the last 5.3 million years. And the last one is that there has to be an additional flux that has a carbonate composition in order to balance the strontium budget. And the conclusions that I take from that is that we can use stable strontium isotope to distinguish between seawater transport and other types of transport, that the fluxes of strontium to the oceans have not increased in both glacials and interglacials, and that there is a strontium flux from the dissolution of carbonates, and that it is a flux that happened during the last 5.3 million years and not just started with the onset of the ice ages. And if we go back to the first diagram here, where I said I want to fill this gap, it means that this is the first curve and this is the second curve. And that's it. Thank you for your attention.
Questions? Yeah, sure. You have a question?
Yes?
So, if the missing flux is the groundwater, that's the brackish groundwater,
Yes?
would you expect during interglacial periods there to be a difference in the hydrological cycle between glacial and interglacial periods, and that would affect the flux of strontium from groundwater?
I think there will be a difference between these two fluxes because we have very different settings if the seawater is going up and down. But what I don't think is that we have the flux of carbonate dissolution that is present just during the glacials and not during the other times. So there is a difference, but this difference cannot be a mega flux that is not there during other times.
Two questions. First, you focus on the Mediterranean.
Yes.
The Mediterranean question is how much is it representative to the global oceans with these isotope ratios? Second, in the glacial period, you have intense rising, frequent rising and lowering of the sea level, and that enhances the exchange with the brackish water. Because the sea level, when it goes down, then the water from the groundwater is going to the ocean again from what was filled earlier with the ocean water. So these two considerations, how do they impact your conclusions?
Okay. So the first one, that...
If you can show the slide to the
Which one? This one? Okay. So about the first conclusion, the Mediterranean, the strontium isotope system has the huge advantage that it takes very long to change and that it will take approximately 2 million years to put everything, and that the exchange within the oceans is much faster. So the assumption is that as soon as we're having an ocean signal, it will essentially be essentially the same all over the world, and that we can measure it in the Mediterranean, and we can measure it in California, and it will be the same.
It doesn't matter that the Mediterranean has much stronger interface with the exchange with the continents than say the Pacific.
No, it doesn't matter because we have much more strontium in the ocean than what comes from the rivers. I have showed you the slide before where I have showed you the sodium and the fresh water, and the seawater is much more concentrated than the fresh water that comes in. So the strontium from the fresh water is not able to dilute the strontium of the seawater that far that we will have an impact. The other one?
The other one is about the rising, perhaps the input from the brackish water should be weighted much higher than the other ones because of the intense, during the ice age fluctuations of sea water, because there is active exchange of the water below the level of the fresh water.
Yes. So in this case, I showed you before two mechanisms, and the one with the clay minerals, which is dependent on how much the interface is moving, will of course be enhanced. But I'm not sure whether the other one, which is just the mixing, between the two, whether this will be enhanced by the moving, because it's just that you mix the two and not how it is moving about. I think it will be essentially the same, how much it moves or not, no matter where the interface is, because it dissolves in the interface, no matter wherever that is.
The flux is larger. That is the point. The flux.
The circulation of seawater?
Yeah, it is enhanced because of the rising load.
Yes, but the thing is that in the carbonate platform, the main dissolution happens within 10% of seawater. So this means if we have less fresh water during the glaciers, then maybe this flux is even smaller.
Indeed, that's that.
Anything more?
It could be. I think we should look at it.
Really enjoyed the talk. So, if I understand right, correct me if I'm wrong,
Yes.
what sets the delta strontium 88 is the proportions, or a big part of it are the proportions between carbonate and silicate weathering, right?
Yes.
So, in a sense, you're not, what you're claiming is that you're not changing these proportions when you go from glacial to interglacial period. I'm asking, I'm not saying.
Okay.
So, so answer that and then I have a follow.
Okay. So I don't think it's not changing at all, because the delta 88, 86 is not as sensitive as the 87, 86, so we can have variations in it. It's just what I want to say is that it will not be that we start with no flux and then boom, we have a huge flux.
Right.
So there will be variations, but there is a limit to these variations.
So follow up on that. You mentioned that grinding of rock by glaciers.
Yes.
And then, the hypothesis of this pulse of weathering is based on A, glaciers grinding of rock, B, later dissolution.
Yes.
Another component that may come into play is the exposure of carbonate platforms during glaciation and sea level drop. Did you consider,
I considered it, so I think that there is an additional flux from that, but in former studies they said that all of the missing carbonate flux comes just from this exposure, and I don't think that this is true, so there has to be a flux also without exposing these carbonate platforms.
Okay, thank you very much.
This was really cool stuff. Really enjoyed it. Did you look at the oxygen isotope composition of these brachiopods too?
No, I did not.
Yeah. Because one of the things that bothers me is that you showed the visor curve at the beginning. And for strontium, it's like super tight. Right? You looked at the oxygen isotope composition, and it's all crazy. It's blown up. And you look at the carbon, same thing. I think that one of the explanations is mostly for the older parts of it, it's diagenetically altered. You go to the Cenozoic, it's the oxygen isotope variation is really.
One more, Rita. Very good talk. You did it, right?
Yeah, no.
She was very excited.
Why do you think is that? Why do you think that strontium, is so well constrained while other elements are not? Or if you have any opinion?
I mean, one thing that I know is that the oxygen isotopes and the carbon isotopes are much more sensitive to what I showed in the beginning, the different parts of the animal.
Yeah.
And that there may be a part of it is just the biocalcification, where we have the animal taking up different parts of strontium, different parts of different oxygen isotope values just from the start.
So I would say that, to mess with, oxygen and carbon are like, what makes, carbonate minerals. Those are like major elements. For oxygen, you can say, okay, this is very sensitive to water, to diagenesis because there's so much oxygen in water. For carbon, it's a problem because you need something really messed up to happen to change the isotope composition of the carbon isotope composition in these materials. Now, my impression is the problem is not so big for Cenozoic samples, but I was wondering, did you analyze any, Mesozoic brachiopods, Paleozoic brachiopods?
I know people from my project did, because the baseline Earth project is all over the Phanerozoic, but I worked just in the very young samples.
So do you happen to know how does strontium 88 to 86 looks like for older samples? Does it behave as nicely, or is it all messed up? That's my question.
88, 86. I showed you at the start. I mean, nice is overstating it.
Yeah, just look at here. What you have. If you plot your data here, right?
It will be here.
And it's here.
Yes.
So I would say this is much more constrained than this, right? So it looks like it's. This variation is not. It could potentially be diagenesis kicking in and
it could be, yes.
messing up the
Yeah.
So an interesting thing is that if you plot the oxygen isotope composition of the same brachiopods, from Weiser and Prokop, or I think maybe it's Prokop and Weiser, variation-wise, you would get very tight variation here, and then it explodes. It would kind of resemble
but
what
the
you see
thing
here.
is that I think with the 87, 86, but I think that it will be less, it will be harder to change this than this is if we don't move the solution that does it.
Yeah.
Then we can have a different fractionation here and with the oxygen isotopes and the carbon, but with the 87, 86 we would not see it.
Yeah, this is one of the things that that I thought that it's interesting, but
you can Uri, you can talk with him hours.
Okay.
Okay, hours. But I wanted to say congratulations.
Thank you.
It was very good. You're excellent. You did the show, and the presentation was very organized. I studied a lot. Thank you so much.
Yeah, I won't keep you for hours. I'm going to. But anyways, what I'm saying is that an interesting thing to do would be to, not look at absolute values, but look at how the variability changes. I think that even here in the strontium, the distribution of values here, if you do moving average and moving standard deviation, is better than here. Right? So, I would be curious to look at how variability looks like when you go back in time, and the obvious culprit is diagenesis, kicking in, and some you let carbonates stay in sediments for more time. Diagenesis will eventually get to them. Yeah, but very cool stuff.
החתירות שם בים המלח. כן, אותו דבר שם.
אותו דבר בדיוק.
מה?
אותו דבר. יאללה, ריטה.
Yes.
Now you can fight against the judges.
Very good.
Now you can go back home, find a husband, bring children to the world.
Yeah.
Yeah, that's it. You did excellent job.
Thank you.
Now you are set up.
Okay.
Not irritated anymore.
Yeah.
Good.
Okay, now you can go to your office and write the paper.
Yes.
Yalla, we go and have some lunch together, and then we have to go to Japan.
לא סידרתי.
מה לא סידרת? אתה לפחות יש לך, אתך מישהו דואג לך בבית, לי אף אחד לא דואג. Rita, it was really very good.
Yeah, very good.
Thank you.
Understandable and fine.
And you can ask them to send the because they are recording you.
Yes.
So you can send it to Tony and to Lucia.
Okay.
Really?
I think Lucia was trying to live see it, but I'm not sure.
Doesn't matter, no. It's so complicated. I found out with all this, I don't understand how people that are doing business, right? All the time they are telling that they are doing these video conferences. You know, we could really never do a video conference in a normal way.
That's true, but in places that they need it, like businesses, they have a special. Yeah, it's very fast. Actually, if you use the G5 system,
I don't know what
it is very fast. You can transfer video very fast and in high quality.
Because this is not science.
We are using it.
We are talking about money, right? When you talk about money, this is serious, you know, how they lose the money, how they gain the money.
So that's important. Well, how do you turn this off?
אתה לוחץ פעמיים.
I'm not sure.
You press twice. Here.
זה לא...
כאן. You switch off here. That's all.
שקונט.
Okay. Yeah, let's go.
Let's go.